Today we're going to talk about heat and heat transfer, and this will be pretty much a review of concepts that we have discussed in the past. I think everything that we're going to discuss today, we have also discussed in basic science, maybe with a little bit of extra discussion, a little bit more complexity, but overall it's going to be very little new material in this week's material. So I think hopefully this will be a nice way to ease back into work after a couple of weeks off. So we're going to talk about heat, and just as a definition, heat is the spontaneous transfer of energy due to a temperature difference. It is also a change in the total kinetic energy of molecules in an object. So in any particular object is made up of a certain number of molecules. If you measure the speed and velocity of every one of those molecules and calculate a kinetic energy, then add all of those molecules' kinetic energy together, then that would be the heat of that object. Now, if you want to look at one comment I do want to make here, that's to be distinguished from temperature. Temperature is the average kinetic energy of the molecules. And so you would take the total heat and divide by the number of molecules in the object, and that would give you the average kinetic energy in an object. So that what that means is the total heat of an object can be high even if the temperature is somewhat low if it's a very large object, just as an example. Now this diagram shows a situation where you have two objects with two different temperatures. You have a Coca-Cola can on the left and a block of ice on the right. They are not the same temperature, and they are not in thermal equilibrium. If they're brought into contact, eventually they will exchange energy in such a way that they both reach the same temperature. At that point, they are in equilibrium, and any energy transfer that occurs will pass from the Coke to the ice and from the ice to the Coke in equal amounts. So the heat transfer occurs because of the temperature difference, and once the temperature difference goes away, then no further heat transfer occurs because it's in equilibrium. Now, obviously, the table and the air around it also is impacted by this effect. In terms of measuring heat, the most common unit of measurement for heat is kilocalorie. This is equal to the amount of heat needed to raise 1 kilogram of water 1 degree centigrade, and obviously it's equal to 1,000 calories. Now this diagram shows the schematic of a machine that was used to calculate the mechanical equivalent of heat. And what that is both mechanical energy and heat energy are forms of energy, and so they can be transferred one to the other. And Joule set this up in such a way as that the weights were allowed to fall, and when these weights fall, you can calculate the change in potential energy, which represents the amount of energy that would then be passed into the water, and then you can measure how much the temperature of the water goes up. And this is known as the mechanical equivalent of heat. And as it turns out, a kilocalorie is equal to 4,186 joules in using this calculation. Now, heat transfer can result in a change in temperature. And in order to calculate the change in temperature, you have to know something about the objects that are involved. Each object, depending on what it's made of, will allow heat to move through it more rapidly or less rapidly. It will take up heat better, or it will not take up heat so well. And the measurement of the ability of an object to take up heat into itself is called the specific heat. And this is actually the heat as compared to water, because basically what it is a measurement of the amount of heat required to raise the temperature of a kilogram of any material 1 degree centigrade. And so what you have in this here is if you add heat to an object, you get a change in temperature. If you double the amount of heat, you'll double the change in temperature. The second diagram shows if you add heat to an object, you get a change in temperature. If you double the amount of heat and double the mass, the change in temperature remains the same. The third shows that if you add the same amount of heat to copper and to water, you get a different outcome because the specific heat of water is much higher than the specific heat of copper. And this is the formula that's used to calculate the change in temperature that will occur with any particular amount of heat. What you see here is Q, which represents the heat that's put into the object, is equal to the mass of the object times its specific heat times the change in temperature in degrees centigrade. And this is a very important formula for you to remember in working your problems. So here are a couple problems that I want to take a look at, and I want to apologize in advance. I don't have one of my pieces of equipment that I normally use, so my writing may be a little bit sloppier. Hopefully I'll be able to do this problem for you. So let's start out with this first problem. We have a 2.26 kilogram object, hot water, excuse me. So let's say we've got a pot with some hot water in it, and it's 2.26 kilograms of hot water, and we know that the water specific heat is 1 kilocalorie per kilogram per degree centigrade. So 1 kilocalorie will raise the temperature of 1 kilogram 1 degree centigrade. And this water is, as it says, hot at 95 degrees centigrade. It's poured into a copper pot. The copper pot weighs 0.875 kilograms. Its specific heat is given here, and the temperature is 15 degrees. So the question is, what is the final temperature of the water in the pot together? So the way to look at this is that the heat, Q, of the water, the heat the water loses, has to be equal to the heat that the pot gains. Okay, so that's what we've got right here, and that is represented by that formula, MC delta T for the water has to equal MC delta T for the pot. Now if we assume that the final temperature is TF, then we can write this equation as 2.26 times 1 times 95. Now the water is going to lose, so we're going to start out with a higher temperature so we don't end up with negative numbers, minus the final temperature, whatever that is. And so that's one of them. And that's going to be equal to the pot's weight, which is 0.87. I guess my handwriting looks a lot about like Seth's right now. 5 times 0.09. Did I say 0.0924? I'm not 24 times, sorry about this, TF Now the TF is going to be higher, so we'll put TF minus 15 degrees. Now I'm not going to write out all of the calculation that I went through, but I will tell you that if you solve this equation, TF equals 92.23 degrees. So it's very close to the temperature of the water. And it makes sense when you look at the fact that water has a specific heat of 1, whereas copper has a specific heat of 0.09. The effect of the copper is going to be minimal on the water. Sorry about the handwriting there, but that's the first problem. The second problem here is the car whose mass is 3,750 is stopped by brakes, and there's the specific heat of the brakes on level ground. Its initial velocity is 35 meters per second, and it's brought to a stop. The brakes weigh 22.5 kilos, and their initial temperature is 22 degrees. What is the final temperature in the brakes? Now, what this is an opportunity to show the transfer of kinetic energy into heat energy. So basically what you're doing is stopping a car, and all of that kinetic energy is going to go into heating the brakes up. And there's a few assumptions here. That is that all the energy goes into heating the brakes. Okay, and so that's the assumption you have to make, and you have to make that's the total weight. The 22.5 kilos is the total weight for the brakes. The other thing is that the average velocity. This is basically a even slowdown, so that the average velocity here is going to be 1/2 of 35, or 17.5. So if we use that, the kinetic energy here is going to equal 1/2 mv squared, where m, and that's going to equal 1/2 times 3,750. This is really not working very well. I'm really sorry about this. Times 17.5 squared. And that's going to be the total kinetic energy that this is the total kinetic energy that this car has to lose. And if you do the calculation, and again, I'm not going to show you all of that, but if you do the calculation here, you get 5.742 times 10 to the 5th. So that's the total amount of kinetic energy in joules that the car loses by stopping. And if we assume that that is transferred entirely, well, wait a minute. If we assume that that's transferred entirely into stopping the car, equals, it'll be m c and delta t again. Okay, so that's going to equal, the mass here is 22.5, and the specific heat is 800 times 800, and then times TF minus, and its initial temperature is 22 degrees. Okay, and again, you're going to have to, if you want to do the math yourself, you can, but if you do this, you get 53.9 degrees, which again sounds about right to me. So what you have here is you're heating up the brakes, and this transfers this mechanical energy into heat energy, and it shows exactly what we were talking about before. So I'm going to stop at this point, and we will move on to the next part of the lecture next.